Hello everyone. Today we will begin with the session 4 of 16th group elements basically. Okay, so I think the students are already there. Everyone is requested to drop down their names for the attendance purpose. Are you guys revising your sessions? Are you people revising your sessions thoroughly? Okay, good. So we'll start with the session now. So today we will discuss about the oxoacids, right? What is basically a oxoacid? Oxoacid of an element, for example, phosphorus we have studied, right? The oxoacid was H3PO4, H3PO2. These were the oxoacids. That means OH group in which the OH group is present basically, that is known as the oxoacid of that particular element. So now we will be dealing with the oxoacids of the 16th group elements. So first, to be very specific, oxoacids of sulfur are important. Oxoacids of sulfur are very important. Selenium and tellurium, you can just remember that which of the oxoacids are formed by selenium and tellurium, right? But the structures, the properties, the chemical reactivities of oxoacids of sulfur is important from the examination point of view. Okay, so first one is the sulphurous acid, that is H2SO3. Next is the parent acid, that is the sulphuric acid, H2SO4. Now this is very important. Peroxomonosulfuric acid, its common name is Carros acid, right? So you have to remember the formula for Carros acid by name. For example, Carros acid, the chemical formula is H2SO5. It is known as Carros acid. Peroxodisulfuric acid is known as Marshall's acid. So, Marshall's acid formula would become H2S2O8. Okay. Thiosulfuric acid, H2S2O3. Dithionic acid, H2S2O6. Pyrosulfuric acid, H2S2O7. So, amongst these, Carros acids, Marshall acid, sulfuric acid, sulphurous acid and thionic acid series is important from the examination point of view. Now, for selenium, if you consider the oxoacids, selenious acid, that is H2SeO3, and selenic acid, that is H2SeO4. For tellurium also, there are tellurous acid and telluric acid, H2TeO3 and H2TeO4 are the chemical formulas for tellurous acid as well as telluric acid, right? Now we come to the structure basically, that is very much important. Structure and the oxidation state. Structure and the oxidation state. So first, if you consider H2SO3, see, whenever you are particularly drawing oxoacids of sulfur, remember that sulfur and phosphorus both are having high affinity of oxygen. Both are having high affinity of oxygen. That means they tend to form basically S double bond O and P double bond O, right? Now, next thing that needs to be considered here, that first, when you will take hydrogen atoms, they will be connected to basically oxygen, right? First, give it a priority that hydrogen atom should be connected to oxygen, and if let us say that the number of oxygen is less than that of the hydrogens, then the rest of the hydrogen you can connect it directly to the central element, right. So these particular things you need to remember, that sulfur and phosphorus will always form double bond O because they are having very high affinity for oxygen, first point. Second one is, try to place all the hydrogens connected to oxygen, and if there are other hydrogens left, in the case where the oxygen number is less than that of the hydrogen, then you can directly connect the hydrogen to the central atom, right. So let us draw the structures now. So if you consider H2SO3, that is the sulphurous acid, so first S will form double bond O, right. Now how many oxygens are left? 2 oxygens are left. So 1, 2. Now if you see that hydrogen should be connected to oxygen first. So this will be OH and OH. So this is the structure of H2SO3. Oxidation state, if you consider, oxygen will be -2 here, so it will give +2 to sulfur because oxygen is more electronegative than sulfur. Then -1 from here, so this will be +1, and -1 for this oxygen, this will be +1, right. So this will consider basically +2 +1 +1, that will be equal to +4. So the oxidation state of sulfur in H2SO3, that is sulphurous acid, will be +4, or you can find it out this way also, +2 plus x minus 6 will be equal to 0. So x will be equal to what? 4. So this is the oxidation state of sulfur in sulphurous acid. Now consider H2S2O5, right. So this means that 2 sulfurs are there. So first let us draw 2 sulfurs. Now always remember that this try to make this structure symmetrical. Try to make this structure symmetrical. Not all cases will have the symmetrical structure, but basically most of these structures are symmetrical in nature, right. So H2S2O5. Now place one double bond O here, one double bond O here. Now as there are 2 hydrogens, so one OH here and one OH here. Now how many oxygens are left? 1, 2, 3, 4, and the one is the 5th one. So this will be here, right. Now why can't we basically put oxygen in between, right. So remember that most of the elements, most of the central atoms basically try to show their maximum covalency. Try to show their maximum covalency. Now anyone can tell me what is the covalency of sulfur? What is the maximum covalency of sulfur? What is the maximum covalency of sulfur? Anyone? What is the maximum covalency of sulfur? Sulfur can form maximum how many number of bonds? How many number of covalent bonds? How many number of covalent bonds can sulfur form? Anyone? What are the maximum number of bonds, covalent bonds, that can be formed by sulfur? This is a basic 11th part. You should know this. Yes, Sham, very good. The maximum covalency of sulfur is basically 6, right? So, if you place oxygen here, let us say, right? Let us say you place oxygen here. This oxygen, let us say you are placing it here in between the 2 sulfurs, right? This is not the correct structure. Why? Because sulfur is showing here the covalency of 5. See how many bond it is making? 1, 2, 3, 4. 4, sorry. And this will also show a covalency of 4, 1, 2, 3, 4, right? And if you draw it this way, basically, that sulfur is connected to double bond O. Now this sulfur is showing its maximum covalency, that is 6. However, this is not showing the maximum covalency, this second sulfur, but one of the sulfur is showing here the maximum covalency. So this is the most appropriate structure amongst the two, right? In the other structure, both were not showing their maximum covalency, right? So this structure is inappropriate, while this structure, if you consider, it is more appropriate. Now consider the oxidation state. So here if you see plus 2 from this oxygen, plus 1 from this, so it will have plus 3. This sulfur will be having plus 3 oxidation state, and this sulfur, if you consider, plus 2 from this oxygen, plus 2 from this oxygen, and plus 1 from this oxygen. So plus 2 plus 2 plus 1, that will be equal to what? 5. Oxygen sulfur is in plus 5 oxidation state. Remember that there is a difference between covalency and oxidation state. Covalency is what? Basically, covalency is the number of covalent bond that can be formed by a particular species. Now next consider H2S2O4, that is dithionous series. So draw it, sulfur here, 2 hydrogens are there. So 1 OH here, 1 OH here, right? Now as sulfur is having high affinity for oxygen and it also wants to increase its covalency basically. So double bond O here, double bond O here, right? Now 4 are completed and it is also a symmetrical structure. So you join sulfur and sulfur basically. If you consider here, because sulfur and sulfur there is no electronegativity difference, so you will not count the oxidation state. There will be no plus minus charge from this bond, but from this bond if you consider, minus 2 to oxygen, plus 2 to sulfur, minus 1 to oxygen, plus 1 to sulfur. So this will come out to be basically plus 3 for each of them. So the oxidation state will come out to be plus 3 for each of them. Or you can do it vice versa also, that plus 2 plus 2x minus 8 will be equal to 0. So 2x equals to 6 and x equals to plus 3. Okay. Now come on to sulfuric acid. Here also if you consider, the 2 hydrogens are connected to oxygen and not directly to hydrogen, right? And 2 double bond O is there. So oxidation state if you consider, it is plus 6 in H2SO4. H2S2O3, that is thiosulfuric acid if you consider, right? So why sulfur is forming double bond here, right? It could also have formed single bond to increase its covalency, to show its maximum covalency, that will be equal to 6, and to basically complete the octet of this sulfur also, right? So this is very important if you consider. Here if you take this sulfur, it is having minus 2 oxidation state. This you have to remember, this one is important. Here if you see, sulfur is having minus 2 oxidation state, and here if you see, sulfur is having plus 6 oxidation state. Now H2S2O7, now consider here sulfur, sulfur, OH, OH, because 2 hydrogens are there. Then you place double bond O, double bond O. Try to draw the symmetrical structure, and also the maximum covalency has been achieved by sulfur, right? So here you will just place oxygen. So this is the structure of pyrosulfuric acid. This is particularly a basic trick how you can remember the structures of oxoacids of sulfur, right? Here if you will count down the oxidation state of sulfur, it will come out to be plus 6. Now thionic acid series. Now what is thionic acid series? This is very important, right? If you consider, basically there are 2 OH at the terminal position, right? That is this group, if you see, this is the terminal position, right? This particular group will be the terminal position, that is basically HSO3 will be the terminal position. Here also HSO3 will be the terminal position, and in between those terminal position you can have a chain of sulfur. You can have a chain of sulfur, right? So here if you will consider, basically the oxidation state of the mid sulfur comes out to be 0, while oxidation state of the end sulfur comes out to be +5. So the terminal sulfurs will have the oxidation state of +5, and the middle sulfur, that is forming the basically chain, that is the sulfur-sulfur chain. N can be 1 also, N can be 2 also, N can be 3 also, right? So this is known as the thionic acid series. So here the sulfur will have the oxidation state equal to 0. Understood, everyone? Is everyone able to get all these structures? Now, next consider peroxoacid series, right? So basically, as the name suggests, it will have a peroxy linkage. So here if you see S double bond O, OOH. First one is H2SO5. Second one is the H2S2O8. Common names we have discussed, Marshall's acid and Carr's acid basically. So they are the peroxoacid series. So here also a peroxy linkage is here, and here also a peroxy linkage is here, right? So this is how you can draw the structure of H2SO5 and H2S2O8. They are named as peroxoacid series because they are having a peroxy linkage here, right? And if you want to calculate the oxidation state of both the sulfurs, calculate it, +2 plus X minus 10. So this will actually come out to be, because it is O2 2 minus here, right? This is O2 2 minus. So here if you will consider +1 from here, and +2 from here, +2 from here, and +1 from here. So it will come out to be +6. Similarly, if you will consider this one, you will have +1 from this oxygen linkage, +2 from this one, +2 from this double bond O, and +1 from this OH. So it will come out to be basically 6. So this is how you can calculate the oxidation state from the structure itself. Now tell me this question: which of the following species does not contain SS linkage? See, if some ion is given like this, you can always write it as H2S2O2. Then you can write it down as H2S2O3. Then you can write it down as H2S2O5. Draw these structures and let me know that which of the following species does not contain sulfur-sulfur linkage. Draw the structures and let me know the answer. A, B, C, or none of these? D. Anyone with the answer? Draw the structures the way I have told you and let me know the answer. No, Sham, re-look at your answer. See, if you consider somewhat, it will be like this: S, OH, S, OH, and then double bond O here. There is a sulfur-sulfur linkage in B. Yes, very good. Nishantini, Nilambari, you are correct with your answers that none of these misses the SS linkage. That means in S2O2 2 minus also, in S2O3 2 minus also, and in S2O5 2 minus also, there are sulfur-sulfur linkage is present. Draw the structure of S2O2 2 minus. This will be S2O2 2 minus. This will be somewhat like this. Sorry. Then S2O3 2 negative. This will be sulfur, sulfur, double bond O, O negative, and yeah, this one will also have O negative. S2O5, if you see, this will also have a sulfur-sulfur linkage, O negative, double bond O, then 1, 2, 3, 4, and then 1 you can always place here, right? So remember, while drawing the structures, first that hydrogen and oxygen will be connected. Complete the covalency of sulfur. Try to complete the covalency of sulfur, right? That is 6. Yeah, you all are correct with the answers. The answer is D. Now we will, yeah, Arun, you are also correct. Sham, you are also correct with the answer. Now here if you see, we will study about sulfuric acid, that is H2SO4. H2SO4. So if you draw the structure of H2SO4, what is it? OH, OH and double bond O. So this is the basic structure of H2SO4. Or if you remove the hydrogens, basically that will be SO4 2 negative, right? So its common name is basically oil of vitriol, and it is the king of chemicals. Now why it is known as the king of chemicals, basically, right? It is known as the king of chemicals because almost all the chemical substances indirectly or directly requires H2SO4 for their formation. Okay. Now its preparation. First we have to prepare SO2. So sulfur on direct heating with oxygen will give you SO2, right? Or if you say iron pyrite, basically if you treat it with oxygen, it will give you SO2. The first step is the production of SO2. Second step, if you consider production of the catalyst, that is basically oxides of nitrogen. So NaNO3 in the presence of H2SO4 will give you Na2SO4 plus HNO3. Now this nitric acid will decompose to give you nitrogen oxides, that is NO and NO2. So these basically act as catalyst in the formation of sulfuric acid. Now these SO2 and these NO2 oxide will combine to form SO3 and NO. This SO3 will react with water to form H2SO4, right? And the NO which is being released basically will form NO2, right? So this is how basically you can manufacture H2SO4. This is known as lead chamber process, right? So first what is done? SO2 is formed. Second, NO and NO2 are obtained. Third, you will just mix up the two, that is SO2 will react with NO2 and it will lead to the formation of SO3. Now this SO3 on reaction with water will give you H2SO4. So this is how basically you can produce H2SO4. Now sulfuric acid is manufactured by contact process. We have done this ton times basically. That what is contact process? SO2 plus O2 with the vanadium pentoxide as catalyst will give you SO3, right? So what is done? Basically sulfur or sulfide ores, that is FeS2 let us take, right? Any two of them are taken and they are burnt in air to give SO2. Now this SO2 is basically converted into SO3, right? Now if you see this reaction, basically the contact process, if you see, it is exothermic in nature as the delta H value is negative here, right? So therefore it is favored by low temperature and high pressure to obtain the maximum yield, right? Because exothermic reactions are most favorable at lower temperature, right? But the temperature also cannot be very low. Why? Because the rate of the reaction also depends upon temperature, that we have done in chemical kinetics, right? So the rate of reaction would decrease otherwise if we will lower the temperature very much. Okay. Now next, now SO3 has been produced through the contact process. Now it combines with H2SO4 to give Olem. It combines with H2SO4 to give Olem, that is H2S2O7. Now when you dilute this particular Olem with water, it gives H2SO4 of the desired concentration. So by this process, basically the H2SO4 you are obtaining is 96 to 98% pure. Okay, and H2SO4 is very corrosive in nature, right? A single drop of concentrated H2SO4 can burn your hand. And if you see in the industry, these two steps, basically the addition of SO3 and H2SO4 to give Olem and dilution of Olem are carried out simultaneously, right? That means the Olem that is produced in the continuous manner, it will be diluted so as to reduce the cost of formation. So these two steps are done in continuation. Now this is how basically sulfuric acid can be prepared. So this is a plant which operates to give H2SO4 of the desired concentration. So the pressure that is maintained in the plant is 2 bar and it has a temperature of 720 Kelvin. So what is done here? Here let us say sulfur particles are there, air is let in, right? So this will give you basically what? That S plus O2 will give you what? SO2, right? Now this SO2 which is being formed here, it is basically impure, right? So we want to remove the dust or the impurities that are present here. So this is the dust precipitator which will remove some impurities. The other impurities will be removed by the water spray here, right? Water will be sprayed and therefore the more impurities will be reduced. Now what is done, that conc H2SO4 is sprayed to remove the water. Basically it acts as a dehydrating agent, so it removes water. Now this dry SO2 plus O2 is passed through arsenic purifier. That means it will remove all the arsenic oxide. It will remove all the arsenic oxide. Then this particular mixture is led into a preheater, right? And here the catalyst, that is vanadium pentaoxide, is added. Now the SO2 plus O2 will lead to the formation of SO3 in the process, in the presence of the catalyst, that is V2O5. Now this particular mixture, that is SO3, will be treated with conc H2SO4 to give Olem, and this Olem is basically diluted to give the 96 to 98% concentrated H2SO4. So this is how basically the plant works in which the H2SO4 is manufactured of the desired concentration. Okay. You can just write down the process in the small steps. First the impurities are removed through the dust precipitator, then the remaining impurities are removed from the water sprayer, then the conc H2SO4 is sprayed basically to remove all the excess water. Then this dry SO2 plus O2 is led through a arsenic purifier which will reduce the amount of arsenic oxide. Then it is passed into a preheater, right? And after that it is passed into the catalytic converter in which vanadium pentaoxide is placed, which is acting as a catalyst. This reaction will give you SO3, and this SO3 on spraying with conc H2SO4 basically will lead to the formation of Olem, that is H2S2O7, right? And dilution of this particular Olem will lead you to the formation of 96 to 98% of H2SO4. Now next, the sulfuric acid is basically colorless, it is dense, it is a oily liquid, right? And it is having a specific gravity of 1.84 at 298 Kelvin. Now this acid has a freezing point of 283 Kelvin and a boiling point of 611 Kelvin. Now it dissolves in water with the evolution of a large quantity of heat. That means dissolution of H2SO4 in water is a highly exothermic process. Chemical reactions of H2SO4 basically are a result of the following characteristics, because it is having low volatility, Second, it is having a strong acidic character. The acidic character is due to the presence of the OH groups, right? Basically, if you see that when H2SO4 will release this oxygen, will release this proton, basically H plus, that will lead to the formation of sulfate ion. So, because of the presence of these hydrogens which are connected to the oxygen, H2SO4 is acidic in nature. It has strong affinity for water and it can act as an oxidizing agent. Obviously, if you consider that sulfur here is present in +6 oxidation state, which is the maximum oxidation state of sulfur that can be shown. Okay, so it will tend to reduce itself. Therefore, it will oxidize the other species. Now, sulfuric acid, if you see, it is ionizing in two steps. First, the removal of first hydrogen, and the second, the removal of the second hydrogen. So, here if you see that first dissociation constant, in which the first hydrogen is basically transferred to the water, giving the hydronium ion and the HSO4 negative. So, it is very much greater than 10. That means the reaction is very fast. Fast means the dissociation is very much favorable. But if you consider the second dissociation constant, it is 1.2 into 10 raised to the power minus 2. That means HSO4 negative is a weaker acid than that of the H2SO4, right? So, if you compare the acidity of HSO4 negative and H2SO4, because dissociation constant of H2SO4 is more than that of the HSO4 negative, therefore, H2SO4 is a strong acid than that of HSO4 negative. Okay. Now, this particular acid can form two types of salts basically, right? Either the normal sulfates or the normal hydrogen sulfate. For example, if you write down sodium sulfate, it will give you Na2SO4, right? And if you get through sodium hydrogen sulfate, so it will be NaHSO4. Similarly, if you want to write down calcium sulfate, it will be this, right? And calcium hydrogen sulfate, it will be what? Something like this, right? So, basically two types of sulfates can be formed, the normal sulfate, copper sulfate, sodium sulfate, and the acid sulfate, that is HSO4 negative. For example, sodium hydrogen sulfate, NaHSO4. You can write down this once, then we will move to the next slide. Okay, so next, action of heat. So, thermal decomposition of H2SO4 will give you water plus SO2 plus nascent oxygen, right. Now, this is why, due to the release of this particular nascent oxygen, it can act as oxidizing agent. So, non-metals are oxidized to their oxide. For example, carbon plus this nascent oxygen, which is released by the decomposition of H2SO4, will give you CO2. Then sulfur on reaction with this nascent oxygen will give you SO2. Then phosphorus will give you its corresponding oxide P2O5. Now, if you treat Ki with H2SO4, here I is of -1 oxidation state. Here if you see, I2 is in 0 oxidation state. So, oxidation of I has taken place. Br is Br negative here and Br2 here. So, Br2 is basically 0 oxidation state. So, -1 to 0, that means that bromine is being oxidized here. So, this is how you can remember the products basically, right, that non-metals will form their oxides, and if you are taking halogens such as iodine, bromine, they will be oxidized to their higher oxidation states. That means iodide to iodine, bromide to bromine. Next, come on to the displacement reaction. It displaces volatile acids from their salts. Now this is very important. Here if you see H2S, HCl, HNO3, H3PO4 are volatile acids, right? So basically it happens that from these salts, these corresponding volatile acids are formed. For example, Na2S will form H2S, NaCl will form HCl, NaNO3 will form HNO3, calcium phosphate will form phosphoric acid. This is how you can remember these displacement reactions. Now next, metals above hydrogen in the electrochemical series, they react with dilute H2SO4 with the evolution of hydrogen. For example, if you see that what are the elements which are above in the electrochemical series, if you see iron, tin, zinc, aluminium, manganese, magnesium, these are above hydrogen in the electrochemical series. So on the reaction with H2SO4, they will yield you metal sulfates plus hydrogen. For example, Fe plus H2SO4 will yield you FeSO4 plus hydrogen, right? Aluminium plus H2SO4 will give you Al2SO4 plus hydrogen. That means corresponding sulfate and hydrogen gas is evolved, which burns with a pop-up sound. Concentrated H2SO4 reacts with all metals except gold and platinum. Gold we have seen that it reacts with aqua regia. That we have also done. So aqua regia is very important. If you are not revising your sessions, I am again mentioning that revise your sessions particularly, right? And some things I have marked important, right? Those particular things you have to keep in mind. They are necessary to be kept in mind basically. So we'll move on to the next. So metal plus conc H2SO4 will give you metal sulfate plus SO2 plus water. So with dilute H2SO4 you will be yielding metal sulfate plus hydrogen gas. But with conc H2SO4 the products are metal sulfate plus SO2 plus water. Now next, dehydrating agent, that means removal of water. So it is a very strong dehydrating agent. Why? Because it has very good affinity for water. It has very good affinity for water. So if you see C12H2, H22O11, it is basically dehydrating carbon. It is known as what? Carbohydrates. Why it is known as carbohydrates? Because initially it was considered that they are basically hydrates of carbon. Therefore, the name came that carbohydrates, right? Now here if you see that carbon is basically being dehydrated and carbon is left, and while these H2O molecules are associated with H2SO4 now. C2H5OH if you will see, it will give you ethane, the water will go on to H2SO4. Formic acid will lead to the formation of carbon monoxide, the water will go on to H2SO4. Oxalic acid if you see, what is the formula for oxalic acid? COOH, COOH. This is the formula for oxalic acid. So oxalic acid if you see, it will give you carbon monoxide plus carbon dioxide and the water will go to the H2SO4. Now what is fuming sulfuric acid? It is the H2SO4 associated with one molecule of SO3, that is known as fuming sulfuric acid. So with ammonia actually it is forming ammonium sulfate, hence ammonia cannot be dried over H2SO4. Now this is very important, it is unable to dehydrate ammonia or basically dry ammonia because of the formation of ammonium sulfate. Now reaction with PCl5. So H2SO4 on reaction with PCl5, it will give you chlorosulphonic acid. Chlorosulphonic acid. That means SO2OH, this part, and chlorine will combine to give you chlorosulphonic acid. Similarly, with PCl5, it can also give you sulphuryl chloride. That means 2 molecules of chloride here. So the structure, if you draw, it will be somewhat like this. SO2OH, Cl. Sulphuryl chloride, the structure will be like this. SO2, Cl2. Sulfonation of aromatic compounds. So if you see benzene, right, and you react it with H2SO4. So here the formation of benzene sulfonic acid, that is benzene with the SO3H group, is known as benzene sulfonic acid. So sulfonation of aromatic compounds take place. This you will learn in organic chemistry also. Next you move on to uses. So it is used in the manufacture of fertilizers, that is ammonium sulfate, superphosphate, right. It is used in petroleum refining, manufacture of pigments, paints, dyestuff intermediates. It is used in the detergent industry. This is important. It has metallurgical applications that you will more learn in metallurgy. The chapter is there in class 12th. It is used in storage batteries. So we have done in electrochemical cells basically, right? In electrochemistry chapter, we had done some examples of cell in which there was H2SO4 also. So it is used in storage batteries. In the manufacture of nitrocellulose products, and laboratory reagent is the famous use of sulfuric acid. It is used in laboratories. Why? Because almost not all, but most of the chemical compounds require the H2SO4 or the indirect use of H2SO4 to be formed. So amongst these, you can learn that it is used in detergent industry, metallurgical applications, storage battery, and as a laboratory reagent. Now give answer to this particular question. Which reaction represents the oxidizing behavior of H2SO4? Which reaction represents the oxidizing behavior of H2SO4? A, B, C or D? Focus on the reactant and products of the reactions and you can easily find out. The ones who are actually paying attention to this particular session should be able to answer this question. Anyone with the answer? Oxidizing behavior. Sham, A, no. Look at all the reactions. No, A is not correct. Look at the oxidation state of phosphorus in A. It is +5 here, and here also it is +5. So phosphorus is not getting oxidized here. The oxidation state is remaining the same. So this is not the reaction which is basically representing the oxidizing behavior of H2SO4. Shivani, yes, you are correct with your answer. The answer is D. Very good. Because I here, if you see, it is having -1 charge, and I here, if you see, it is having the oxidation state of 0. So for -1 to 0, iodine is I minus is basically getting oxidized because there is an increase in the oxidation state here. While if you consider these two examples, NaOH and NaCl, they are the examples of basically forming the acid from their salts. NaCl, if you consider, we have done this before, that it is releasing corresponding volatile acid, right? And this is basically a acid base reaction. If you see NaOH plus H2SO4, this is a base, this is an acid. So it is basically depicting, the second one is depicting the neutralization reaction. Neutralization reaction. Third one is basically depicting what? The release of volatile acids from its salts. Volatile acid from its salt. And the D1, that is in which the I is getting oxidized basically, is the example of the oxidizing behavior of H2SO4. Yeah. Sham, Shashank, CR Lakshmi, you all are correct with your answers. That answer is D. Good. Now give answer to this particular question. Yeah, CR Lakshmi, you are also correct with the answer. Give answer to this particular question. Conc H2SO4 can be used for drying ammonia gas. Statement 2. Conc H2SO4 shows very good dehydrating property. Answer to this particular question. This also we have discussed. If you are paying attention in the class, you must know the answer to this particular question. Anyone with the answer? Okay, Arun is saying A. No. Can concentrated H2SO4 be used for drying ammonia gas? Yeah, Shashank, you are correct with your answer. The answer is D. Because conc H2SO4 cannot be used for drying ammonia gas. Why? Because it forms ammonium sulfate. It forms ammonium sulfate with ammonia. Therefore, we cannot dehydrate ammonia gas, or basically dry up ammonia gas. Statement 2 says conc H2SO4 is a very good dehydrating agent. Yes, it is a very good dehydrating agent, but not for ammonia. Ammonia is an exception. Yeah, Shashank and Shraddha, you are correct with the answers. That statement 1 is false and statement 2 is true. Good. Yeah, CR Lakshmi, you are also correct with the answer. Shivani, you are also correct with the answers. Now, we'll come on to sulphurous acid. So, we don't have to study much. for these acids. Basically H2SO4 was the more important acid that we need to study, and the structure of all acids are important, right? All oxoacids of sulfur. So sulphurous acid, if you see, basically it is H2SO3, right? So if you look onto the hybridization, basically there is one lone pair, and two oxygens will donate single electrons here, and one oxygen is forming one sigma bond and one pi bond, right? So if you consider the hybridization, it is sp3 hybridization, with a lone pair. Now if you see, SO2 is very soluble in water. Mostly it is present as SO2 plus H2O. Sulphurous acid may exist in the solution in minute amounts. Now this is very important, that SO2 on reaction with water basically gives you H2SO3. Here if you consider the salts of sulphurous acid, that is sulfites, calcium sulfide, barium sulfide, silver sulfide, they are insoluble or are sparingly soluble in water, right? They do not solvate in water. However, if you see sulfides of group 1 metals, for example, if you take sulfite of sodium, sulfite of lithium, right, they are soluble in water, and ammonium sulfite is also soluble in water. So if you see sodium sulfide, it is an important industrial chemical, right? So let us see that how it is particularly formed. Sodium carbonate on reaction with sulfur dioxide will give you sodium bisulfite. Now this sodium hydrogen sulfide or bisulfite basically reacts with again Na2CO3 to form sodium sulfite, that is Na2SO3. This is how basically sodium sulfite can be prepared. Now this sodium sulfite is basically used to bleach the wood pulp, right? Actually from wood pulp we can obtain paper. What is bleaching? Basically lightening of wood pulp. Reducing the color of wood pulp. Okay, it is known as lightening of wood pulp. So Na2SO3 bleaches the wood pulp. It is used to lighten the wood pulp, which further is used for making paper. Now coming on to the oxohalides. So these are the thionyl compounds, basically SOF2, SOCl2, SOBr2, amongst which SOCl2 is very important and it will be used in your organic chemistry as well. So thionyl chloride, it is known, right? So how it is formed? PCl5 on reaction with SO2 will give you thionyl chloride plus POCl3, right? Now SOCl2 on reaction with water basically gets hydrolyzed to give SO2 plus HCl. So most of the thionyl compounds, whether SOF2, SOCl2, SOBr2, basically hydrolyze in water, but SOF2 hydrolyzes slowly. If you consider the structure, if you see, there is one lone pair, halogen will be here and a double bond. Right. Now consider the oxidation state. If you will consider, this will be +2 from this oxygen, +1 from this chlorine, +1 from this chlorine. So this will give you oxidation state of +4. So amongst these thionyl compounds, SOCl2 is important from the examination point of view. Boiling point, melting point, you don't have to remember. Only one temperature I guess you need to remember, that is the transition temperature, right? I guess it was in monoclinic sulfur and rhombic sulfur, the transition temperature was there, that you have to remember. And for others, melting point, boiling point are of no use, because one cannot mug up all the boiling points and the melting points of all the compounds. So they are not asked in the exam itself. Now sulfuryl halides, that means two halogens are there, SO2F2, SO2Cl2, SO2FCl, SO2FBr. So in these two you see the halogens are the same, but here if you see the halogens are different, fluorine and bromine, fluorine and chlorine. So sulfuryl chloride, if you see SO2Cl2, it is a colorless fuming liquid. So SO2 plus Cl2 in the presence of catalyst will yield you SO2Cl2. it is used as the chlorinating agent. That is the important property of SO2Cl2. That also you will learn in organic chemistry. Basically, it is used to chlorinate compounds. Sulfuryl fluoride, it is not hydrolyzed by water, right? Sulfuryl halides have a distorted tetrahedral structure. This we have already done here, that it is a tetrahedral geometry, but due to the basically lone pair bond pair repulsion and other repulsions that are taking place in this structure, the structure is not perfectly tetrahedral but distorted tetrahedral in nature. Yeah, so that's all for today. We are done with the session. You can just once write it down and then we will end up the session for today. Any questions you want to ask? I'm again repeating, structures of oxoacids is very important from the examination point of view, whether it be of sulfur, whether it be of nitrogen, whether it be of phosphorus. Oxide structure is also very important in case of nitrogen. If you see, oxidation state is very important, which is acting as a reducing agent, which is acting as a oxidizing agent. That properties are important basically, right? Now the allotropes are important, allotropes of carbon, allotropes of phosphorus, right? Allotropes of oxygen that we have done, they are also very important from the examination point of view. Yeah, so I think that's all for today. Keep revising your sessions. I'm again repeating, otherwise there will be a condition where you have to leave this particular whole chapter, right? Because it will act as a burden on you. Okay, so that's all for today. Happy learning to all.